Hola. Yo no hablé español la semana pasada. Por lo tanto, uh, yo olvidé mucho. Sorry if I busted your eardrums with that sneeze. Lo siento. I'll wait for a few more viewers and then I'll get started. Okay. Hello, everyone. Welcome back. Hope everyone had a nice Thanksgiving vacation. So, a couple of announcements. Your let's see. So, I think your triad grades are due on um, tomorrow night. So, if there are any assignments that I haven't graded, that any assignments that are in your gradebook in Q that I have not graded yet, you need to send me a Canvas message so I know where to look. Remember, your Q gradebook is the official gradebook. So Canvas is not your official gradebook. Q is. So the grade that you have in Q is the one that you will ultimately receive, not your Canvas one. The other thing is your midterm is available today. It's due next Monday. So I think that's it for the announcements. I did make the assignments quite short. I think they're just like 2 questions this week just because of the midterm. So, let's get started on content. So, let me just refresh your memory. So last time we learned about the concept of we learned about thermal physics, and the main equation was Q equals mc delta T. Okay, so Q is the heat added to a sample. Okay, M is the mass of the sample. C is called the specific heat capacity. And then delta T is the change in temperature. Okay, so we can see because it's kind of useful to rearrange this. We can see that Q over mc equals delta T. So we can see that the larger the specific heat capacity is, the smaller the change in temperature. So things with a large specific heat capacity don't change temperature as easily as things with a smaller specific heat capacity. All right? We applied this equation to calorimetry problems. And for calorimetry problems, the equation is 0 equals Q1 plus Q2 plus ... And this is a reflection of the fact that energy is conserved. So that if one object gains 5 joules of heat, then the other objects have to lose 5 joules of heat collectively. Okay? So that's why Q1 plus Q2 has to equal 0. All right? So that's what we learned about last time. What I want to talk about today, this equation is only valid. Q equals mc delta T is only valid if there is no phase change. Okay? So let's talk about what is a phase change. Well, first thing I want to talk about is what is a phase versus a state? Because you can talk about states of matter, or you can talk about phases of matter. So a state of matter is less descriptive. State is just solid, liquid, or gas. However, a phase is more general. Because did you know, for example, that ice, there are over 10 different types of ice. I don't know how many different types there are exactly, but depending on the pressure and the temperature, there are different forms of ice. Those are all the same state. Ice is the solid state of the chemical water, but there are different phases of ice. Okay, so when I say phase, I mean a specific molecular structure, a specific arrangement of the water molecules is a specific phase. Okay, so that's an important distinction. So, for example, steel has different phases depending on temperature. It's all solid steel, but it's different atomic arrangements in different different phases. So this is only valid if there's no phase change. So I prefer to use the word phase because it gives more information than state. But let's just talk about the gas state really fast. More general is the word. This says more general. Let me zoom in. So for a gas, you should be able to draw what a gas looks like at the molecular level, okay? So if you were to look at a gas at a molecular level, you would see the atoms are far apart, okay? So the atoms are far apart. And that's, of course, a relative term. It's far apart compared to their size. Okay? So, you have to be careful there because it depends on... they're far apart, so they're many atomic spaces apart. But on the human scale, they're obviously the atoms are still really, really close together. The other thing is that the atoms are moving fast. Okay, so they're zipping around. Their velocities are randomized. You've got atoms moving in all different directions with different speeds, and they're moving fast. Okay. So this is a gas. What if we look at a liquid? So for a liquid, the atoms are a lot closer together. Okay. So the atoms are much closer. Okay. And this explains why gases are usually are compressible. You can take a gas and you can shrink it down into a smaller volume, but it's much harder to do that for a liquid because there's just not as much space between the atoms. Okay, but atoms are still, or I should say, atoms have random positions. So a liquid is more or less the same thing as a gas. It's just the spacing between them is a lot less. Okay, so they still have random positions, just like in a gas, but it's just there's a lot less space. So in fact, yeah, liquids and gases are very similar to each other, but because liquids have much less space, they're much less compressible. Can liquids be compressible? Yes. Water is compressible. It's just it takes a lot of pressure to compress water. Okay, the water at the bottom of the ocean is actually denser than the water at the top of the ocean because it's experiencing higher pressure. The atoms are moving. But not quite as fast as in a gas. And furthermore, they're more of jiggling because if we look at a gas, the atoms can really travel a great distance before bumping into something else. But in a liquid, you don't have a lot of space, and so what happens is the atoms are constantly bumping into each other. Okay, and so I would describe it more as a jiggling. Okay, or if you can imagine sort of walking around and if you were dizzy or you were off balance, that's sort of what an atom is doing when it's in the liquid phase because it's bumping into stuff constantly. Okay, so imagine you were like dizzy and walking through a maze in the dark. That's kind of the path. The path that you would take through that maze is similar to the path that atoms are taking in a liquid. If we look at a solid, the atoms are not that much closer together than a liquid. And actually, in some special liquids, the solid is actually less dense. For example, water, the solid is less dense than the liquid. But the defining feature of a solid is that the atoms, oh man, I messed this up. Focus on drawing my picture here. The defining feature of a solid is that the atoms form a regular structure. Okay, so there, in this case, I've drawn it as arranged in rows. Okay, this is actually called the hexagonal close packed crystal structure because you can see that for every one atom, it has 6 around it. Okay, you could have other lattices called. Well, let me just finish my sentence here. Atoms form a regular structure called a crystal lattice. Okay. And so this example right here is what's called a hexagonal close packed. Because it's called hexagonal close packed because each atom has 6 neighbors around it. Okay. You could also have what's called a cubic structure where basically you have 4 nearest neighbors. So this isn't quite the same structure. Okay. So what defines different phases of a solid is when you have a different crystal structure at the atomic level. Okay, so the different forms of ice have different crystal structures. All right. So it might, when you go from ice 1 to ice 2, you might go from hexagonal close packed to cubic or something like that. So depending on the environmental conditions, a certain crystal structure is favorable. Okay. All right. So you can have what's called a phase transition. Okay. And phase transitions happen when heat is added or removed from a sample. So you have gas, or gag for some reason. Gas, liquid, solid. Okay. So if you go from a liquid to a gas, that is called vaporization. Okay. If you go from a gas to a liquid, that is called condensation. All right. If you go from a solid to a liquid, that is called melting. If you go from a liquid to a solid, that's called solidifying or freezing. Freezing is kind of more just for water. If you go from a solid to a gas, that is called sublimation. And if you go from a gas to a solid, that is called deposition. Okay, so these are different phase transitions that can occur. All right, so I want to take that Q equals MC delta T. All right. And I'm going to play around with this equation here. Q equals MC delta T. Let's play around with this equation here. So, all right. if I divide both sides by MC, I get Q over MC equals delta T. All right. And then I'm going to write delta T as T minus T initial. So instead of T final, I'm just writing T. Okay. And then I'm going to add T initial to the other side. And I have T equals 1 over MC times Q plus T initial. All right. So I want to compare that with y equals mx plus b. All right. So if I made a graph of temperature versus heat added, or I should say final temperature versus heat added, I can see that this is the equation of a line. See, T is on the vertical axis, so T is like y. Q is on the horizontal axis, so Q is like x. So this is the equation of a line. All right. Okay. And the number in front of x is the slope. So similarly, the number in front of q is the slope. So the slope of this line is 1 over mc. All right. And then the number that's added on to the end is the intercept. So the intercept is initial temperature. All right. So this is when you are not changing phases. So you add heat, the temperature changes. But once you start changing phase, the temperature stops changing. Okay? So what you will see is that this graph stops increasing and it plateaus. Okay? So maybe this is heating a liquid. Okay? And then once it plateaus, you are now vaporizing the liquid. So when you see a plateau in the temperature versus heat added graph, you are changing the phase, okay? So the temperature stops increasing. So this is what's happening if you boil a pot of water, okay? If you boil a pot of water, the temperature of the water goes up, 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 until it starts to boil. And the moment it starts to boil, you are now vaporizing the liquid, and the temperature is constant at 100 degrees Celsius. Okay. Why is the temperature constant? Well, what would happen if you raised the temperature to 101 degrees Celsius? Then the entire thing would be gas. Okay. So if you had it at 99 degrees Celsius, it wouldn't be changed. It would be all liquid. Okay. So the only temperature at which both phases can coexist is at that one specific temperature. Okay. So because when the pot of water is boiling, you have both water vapor and liquid water coexisting, the temperature is staying at that constant value. Okay. So this temperature at which the plateau occurs is the boiling temperature, T sub B. All right. And what's happening here is on the left part of this graph, you have basically 100% liquid. Okay. And on the right part of the plateau, you have 100% gas. So basically, you add heat, you get a transfer from, the temperature remains constant, but you get a transfer from liquid to gas. It's the same atoms, they're just rearranged differently. Okay? And then once you have 100% gas, now the temperature is going to start to increase again. All right? And the slope will be 1 over mc again. But here's the thing. This C is the specific heat capacity of the liquid phase of that material. But now we have gas in this segment. Okay? So we have the specific heat capacity of the gas phase here. All right? So the key idea here, during a phase change, the temperature is a constant. Okay? During a phase change, the temperature is a constant because the heat. Now remember, temperature is a measure of kinetic energy. So generally speaking, if we add heat, we make the atoms vibrate more quickly, which raises the temperature. But when you are doing a phase change, the heat that you're adding, the energy that you're adding, is not making the atoms go any faster. What it's doing instead is it is rearranging the atoms. Okay? So during a phase change, the temperature is constant because the heat is rearranging the atoms. So it's changing the potential energy of the atoms. Right? Because potential energy is the energy of position. So we're the heat because heat is a form of energy, is rearranging the atoms. So it's changing the potential energy instead of making them go faster. And remember, more speed means changing the kinetic energy, which is the same thing as temperature. Okay? So that's what's happening during a phase change. So what happens is, if you're heating liquid water, for example, as you add heat, the atoms are jiggling more and more quickly. And then once you reach the boiling temperature, then you add heat, and then atoms start to separate and go up into the air. All right? So what does this whole graph look like? If we were to do this graph over a larger range of temperatures and heat added, it would basically look like this. All right? So here you have a solid that you are heating, and then you melt the solid. That's what this first plateau represents. And then you have a liquid that you're heating, and then you boil it, or you vaporize it, whatever you want to say. And then you have a gas. All right? So this first plateau occurs at the melting temperature. The second plateau occurs at the boiling temperature. All right? The slopes are related to the specific heat capacity. So the slope is going to be 1 over mc. All right? Where the specific heat capacity is the specific heat capacity of that particular phase. So solid, liquid, or gas. Okay. So now let's talk about the heat that you need to change the phase. So Q, the equation is Q equals mL. So Q, in this case, is the heat required to change the phase okay. M is the mass of the sample. And then L is called the specific latent heat. And it can be of fusion or of vaporization. Okay, so it takes a different amount of heat to melt a material versus to vaporize a material. Okay, so basically, do you see how the width of this plateau is? This plateau is wider than that plateau. That means that the specific latent heat of vaporization is greater than the specific latent heat of fusion. So the specific latent of fusion controls the solid to liquid transition, and the specific latent heat of vaporization controls the liquid to gas transition. So because this is a wider plateau, that means that the specific latent heat of vaporization is greater. So in this particular example, L vape is greater than L fusion in this case. All right, so this is our main equation for today. All right. The units of specific latent heat are joules per kilogram. So how many joules does it take to change the phase per kilogram of material? All right. So there you have it. So let's talk a little bit about phase change calorimetry. All right. Suppose you have 3 kilograms of water at you have 3 kilograms of water at, let's say, minus 30 degrees Celsius. How much heat is required to raise the temperature to, let's say, 150 degrees Celsius? All right. So if we think about that, negative 30 degrees Celsius water, that is solid because it's less than 0 degrees Celsius. Okay. And 150 degrees Celsius is above 100, so that's going to be a gas. So see how we're going to have phase changes happening. It's going to, as we raise the temperature, it's going to melt, and then we'll be heating a liquid, and then we're going to be boiling a liquid, and then we'll have a gas. Okay? So the total heat required is the heat required to warm up the ice to its melting temperature, plus the heat required to melt the ice, plus the heat required to warm the liquid, plus the heat required to vaporize the liquid. Now, after we vaporized it, it'll be some liquid or some vapor at 100 degrees Celsius, but we want to get to 150. So we have to go ahead and warm the gas now. So you see how we actually have 5 steps. Now, these two that I put stars over, these are the phase changes. So they're going to be governed by ml. Okay. The other ones are not phase changes. They're just heating something within a particular phase. So those are going to be governed by mc delta T. All right. So if it's a phase change, you use ml. If it is a heating a particular phase, you use Q equals mc delta T. All right. So what if we warm the ice? Okay. If we warm the ice, then we're going to use m, which is 3, times c. This I'm not going to, in the interest of time, I'm not going to look it up, but we will look up the specific heat capacity of ice, times delta T. So what is the delta T to warm ice from negative 30 degrees Celsius to its melting temperature? All right, someone type it in. What is the delta T to go from negative 30 degrees Celsius to the melting temperature of ice? Excellent. We got to go 30 degrees to go up from negative 30 to 0. So the delta T is 30. Then I have plus ml, so plus 3 times L. And I will use the specific latent heat of fusion of ice, or of water, I should say. Okay. Now I'm warming the liquid, so I have mc delta T. So I have 3 times the specific heat capacity of liquid water is 4,186 times the delta T. What's the delta T to warm liquid water from its melting temperature, or its freezing temperature in this case, to its boiling temperature? What is its delta T between freezing and boiling for water? 100. Very good. So we raise its temperature by 100. Then we have to vaporize it, so we have 3 times L vape, which would be given, or you'd look it up or whatever. So after we vaporized the liquid water, we now have water vapor at 100 degrees Celsius. So now we have to heat the gas, the water vapor, from 100 degrees Celsius the rest of the way to 150 degrees Celsius. So that's going to be 3 times the specific heat capacity of water vapor, so I'll put WV, times, and what's our change in temperature to go the rest of the way? $50. Very good. Okay, so in the interest of time, I'm not going to look up what these 4 constants are. They're just properties of liquid water. You can look them up in a table. So that equals whatever. The important thing about this is the process of, what do each of these terms mean and why are they there? Okay. We'll do one more example. All right. So let's suppose you have um, 0.4 kilograms of tea. Now, tea is basically water. I mean, I'm sure that offends some of you if you're like, oh, tea is not water. Tea is an amazing beverage, but from the thermodynamic standpoint, tea is basically water with a small amount of additive to it. So it it behaves in terms of its reaction to heat the same way as water does, more or less. Um, it tastes a lot different than water, but in terms of thermodynamics, it behaves much like water. You have 0.4 kilograms of tea at um, and it's at 95 degrees Celsius. Okay. That's too hot to drink. You're going to burn yourself. Okay. So we'll do what my grandma did, which is add ice to her tea. Okay. You add ice to the tea. To cool it. And I should say the ice starts out at 0 degrees Celsius. Okay. This has always bothered me. You ever say, like, oh, we're going to give you an ice cold beverage? Well, that kind of depends on how cold your ice is, because ice can exist at any temperature below 0 degrees Celsius. So if someone says it's ice cold, well, I say, well, how cold is your ice? You know? You add ice to the tea to cool it to, let's say, 40 degrees Celsius. What mass of ice is required? Okay, so this is a calorimetry problem. It's a phase change calorimetry problem. And so because we have two things, we're going to use their fundamental equation. Q0 equals the heat added to the ice plus the heat added to the tea. Now, because the tea is warmer than the ice, basically the Q of the tea is going to be less than 0. It's going to lose heat. The tea is going to lose heat. Okay? And the ice is going to gain heat. Now, what is that heat going to do to the ice? First, it's going to melt the ice. Okay? And then, once the ice is melted, it's going to heat the liquid to 40 degrees Celsius. Okay? So the ice is going to be melted. Now, why doesn't the ice need to be heated up? Because it's already at its melting temperature, so it's ready to melt right off the bat. Okay? In this example, this example right here, the ice was colder than its melting temperature, so we had to heat it up to its melting temperature and then melt it. Okay? Here, it's already to melt. So we melt it and then we heat it up to 40 degrees Celsius. Okay? And then we have the heat of the tea. Now, why are we heating the ice up to 40 degrees Celsius? It's because the ice and the tea are going to reach thermal equilibrium. Thermal equilibrium means we have the same temperature. Okay? Okay, so let's look at this. Melting the ice. That's going to be M times L fusion. To heat it, it's going to be M times the specific heat capacity of the water, because ice will become water, times delta T, which is going to be 40. Because once we've melted the ice, okay, it's going to be water at 0 degrees Celsius. So now we have to take it from 0 degrees to 40 degrees. Then we have the mass of the T, which is 0.4, times the specific heat capacity of the T, times the change in temperature of the T. So the T goes from 95 to 40. All right? So that's a temperature change of minus 55 degrees Celsius. Now, when you're doing temperature changes, it doesn't matter if you have degrees Celsius or Kelvin, because the size of 1 degree of Kelvin is the same as the size, or I should say the size of 1 Kelvin, because we don't say degrees Kelvin, is equal to the size of 1 degree Celsius. So, for example, water will melt at 273 Kelvin and it'll boil at 373 Kelvin. That's a difference of 100 Kelvin. It will melt at 0 degrees Celsius and it'll freeze at 100 degrees Celsius. So still a change of 100. So when you're doing changes in temperature, it doesn't matter if you have Kelvin or degrees Celsius. So now let me plug in. So T is basically water from a thermodynamic standpoint. So its specific heat capacity is 4,200. Okay. And keep in mind, this M is the mass of the ice. So this is what I'm solving for. The ice is water, so that's also 4,200. And now I guess I better look up the specific latent heat of fusion of water. I believe it's 343,000. Let me look it up. Hey Siri, what is the specific latent heat of fusion of water?
Okay, I found this on the web for what is the specific latent heat of fusion of water. Check it out.
I'm going to ask Wolfram Alpha. Typing into Wolfram Alpha. Oh, I was right. Oh, wait. Yeah. 334,000. Damn right I know my specific latent heat of fusion of water. Okay, so we can see that we collect like terms here. And then we can solve for M. So I'm not going to show the math in the interest of time. What we get is the mass of ice is 0.18 kilograms. If you add that mass of ice, then you will have tea at the perfect drinking temperature afterwards. All right, class, that is my